Hello everyone, my name is Mohammad Zainul Abidin, and first of all I would like to welcome you to the very first online session of Mechanics of Materials. If you can recall, before the vacation we have been studying this second chapter, stress and strain axial loading, and we have gone through some of the basic concepts related with stress and strain. We have seen the definition of stress and strain already, and we started our discussion related with the tensile testing machine. In case of tensile testing machine, we have discussed at length what are the various outputs of the tensile testing machine. And if you remember, they were the time, force, and displacement. So I'm gonna continue my discussion from that point onward. Just a brief review of the Hooke's law, and we have already known that all deformable materials, they deform under different kind of load, and this Hooke's law actually refers to the deformation of the material in elastic region. And in elastic region, we already know that the sigma is proportional to the strain, and sigma, where the constant of proportionality is your E, which is actually the modulus of elasticity. So this law holds only in the elastic region as long as the material deformation with respect to the stress is linear. Now on this slide, a typical stress strain test setup is being shown. The machine which you can see on the left of the slide, this one is actually a tensile testing machine. It holds the specimen in the center with the help of two jaws. One of these jaws is fixed and the another one is movable. Sometimes in some machine the lower jaw is movable, in some machine the upper jaw is movable. Anyhow, the objective is to keep the specimen fixed at one end and measure the displacement of the other jaw with respect to the force. Now, the force sensor is also installed on this machine. The objective of the force sensor is to record the force values at different time intervals and also record the values of displacement. Instead of measuring the displacement of the jaws, there is another possibility that exists. It is the usage of extensometer. In this diagram, for example, you can see an extensometer which is installed between these 2 points. For example, this one, the one of the points is here, another point is here. It can be called as the gauge length, which is actually can be represented with the help of L, and dividing this gauge length with the change in length, actually the change length with the gauge with this gauge length will give you the strain values, and dividing the force with the cross section area will deliver you the stress values. Anyhow, the objective if this test is to first of all get a force displacement curve. This force displacement curve looks something like this one. I'm gonna draw it here. Now, if we only draw for the elastic region, for example, then you will have the value of F at the y-axis, and here we can write U, which is, I don't know why it is not writing U, yeah. Now, this force and displacement, the curve between this force and displacement in the elastic region gives you a slope, a consistent slope, which is dependent upon, obviously, on the geometry as well. This slope is called as this slope is called as, sometimes it is given the letter K, or capital K, the stiffness of the material. Now, the stiffness of the material, we can use it to obtain the Hooke's law, such that we can write here, sorry, F, God, what is with this? Something is totally messed up here. I'm sorry about the interruptions. F equals K U. Now if we divide this F by the original area on this side, and this K, I divide this, for example, by the dividing these two things will obviously this side divided by a divided by area and L divided U divided by L will obviously change this vector of proportionality, constant proportionality K, and in our case we call it E, which is the Young's modulus. And finally, here I'm sorry I cannot write the symbols with this available software, so sigma will be equals to E dot epsilon. This should be understood that sigma refers to the stress and epsilon refers to the strain. So I can write that as well. Stress equals Young's modulus times strain. Now this is what we want to obtain. Now using this stress and strain and this formula you have already seen, it's Hooke's law. We can draw another curve, which is the curve between stress and strain, and only the axis values. Okay, now that's what we get from the tensile testing machine. We get force displacement curve, and from that force displacement curve we convert it into the stress strain curve. Here you can notice that on the y-axis we have the stress, and on the x-axis we have strain in both the curves, here and here. But there is a slight difference between both the curves. You notice this red line for the first curve, which is shown on the left. At the bottom it is shown as the curve A, low carbon steel. It peaks up to a certain point. That point is actually called as a yield strength, or it can be denoted as the sigma y. There is a very sharp yield strength point in this curve. This curve then drops a little bit. It remains almost a little bit constant to the, or it remains parallel to the x-axis. Then it keeps on increasing till the maximum point, and that point is actually called as sigma u, or the ultimate tensile strength. Beyond this point, the necking, the region which is called as the necking, it starts, and necking is actually restriction or the reduction of the area from the center. Here you can see in the sample on the extreme left side, you can see this sample where the reduction of the area is very significant. It makes a form of a neck. So the necking starts actually at this point until the specimen breaks or the fracture takes place, like it is shown here in the second image. Now this is a typical stress strain curve of a ductile material, which is actually a low carbon steel. However, in some other cases such as aluminium alloy, which is also a ductile material, we do not observe a sharp yield strength point here like this one, which is observable in this curve. It is not observable here. So in this case, what do? There are certain methods. Sometimes we use an offset method of 1% or 2% offset from the initial value. Anyhow, the remaining or the other parts of the curve, they are almost the same except for this sharp difference of yield strength in both the curves. What are those parts? Before sigma y, we have elastic region or a straight line, which is actually obeying the Hooke's law, and where sigma is proportional to epsilon, and we have the Young's modulus. Beyond this point, the curve, its strain hardens up to the point of the ultimate tensile strength, and beyond ultimate tensile strength, the necking region starts until the specimen breaks or it fractures. Now this is a typical example of a stress strain curve for a ductile material. However, if the material is not ductile, what do you think? And allow me to just show you how we can get. There is no point of asking you because this is going to be a recorded lecture. So I'm gonna draw it here. That if our curve or the material is not ductile, if the material is brittle, what do you expect? Well, this is what we expect. We have sigma here. I'm going to write just sig for convenience, and we have epsilon here. So I'm going to write, once again, it's the same problem. The slide keeps on moving. Anyhow, now eps for epsilon. In a brittle material, this curve starts from this point 0, and it keeps on increasing It remains, in most cases, it remains almost straight, like it follows the Hooke's law. And at certain point, like a point here, this one, at this point, it breaks, it fractures. There is no plastic deformation at all. This is the most important and the most significant difference between the deformation of ductile material and the brittle materials. The ductile materials, they move beyond the point sigma y here. They go onward. They show the plastic deformation, and then after some necking, they show the rupture or the fracture of the specimen. Whereas the brittle materials, they do not show any plastic deformation, rather they break or they fracture, the rupture at the end of elastic deformation. There may be very few cases in literature where even the brittle material shows just a little bit, very little bit, maybe 1 to 2% of the overall of the total deformation. They may show some plastic deformation, but still they are considered as the brittle material. A purely brittle material will not show any plastic deformation. That's for sure. Now, just let's move on to the next slide. On this slide, you can see an example of the brittle material. You have sigma, epsilon, the same thing which I have shown previously, sigma, epsilon here. The only difference is the line which I have drawn, it was straight, it was like linear, whereas in this case for some brittle material, maybe the line can be a little bit curved. We can call it a non-linear elastic behavior. Anyhow, whether it is linear or non-linear, we assume that the Hooke's law holds and sigma is proportional to the epsilon throughout the elastic deformation, where the constant of proportionality is the Young's modulus. Okay, now the next important thing which you should observe at this point is the look at the fracture morphology. This is a typical fracture in a brittle material. You can see there is absolutely no necking region present in the case of this fracture. Here, previously what we have seen, it was the ductile material. It shows some necking before fracture. While in case of brittle material, there is absolutely no necking at all, and the material simply fractures from in between the gauge length. Anyhow, we move on from this point, and we would like to now focus our discussion towards the Hooke's law or the modulus of elasticity. Allow me to erase the previous stuff. Now that's gone. A few more things about the modulus of elasticity. As long as we have material which is almost the same, here the example which is taken is of several different steels. They may have some difference in their composition, but the effect of difference in composition, like we have pure iron, carbon steel, low alloy steel, tempered alloy steel, it only shows the difference in their sigma y value in first place. Sigma y, which is here, which is supposed to be here. This is the region, this is the point for sigma y or the yield strength for the pure iron. This one, for example, the yield strength for carbon steel. Then we have the yield strength for high strength low alloy steel, and then we have the yield strength for the quenched or tempered low alloy steel. Quenched or tempered alloy steel, doesn't matter whether it is low alloy or high, it doesn't really matter. Anyhow, so the very first difference is the point at which the plastic deformation starts. Pure iron, it has a very low yield strength. However, you can observe that its plastic deformation region is actually largest of all the other alloys. Look at the point of fracture or the strain at the point of fracture or the point of rupture. It is more than any other strain value at rupture for any other alloy or any other material. Now, first of all, what is the basic difference between this pure iron and this carbon steel? Obviously, pure iron has no carbon in it. Carbon steel is simply, it has some carbon, maybe up to 0.8 or up to maximum up to 2%, because the steel cannot have more than 2% of carbon. So what is the effect of carbon? It increased the yield strength, right? And it also increased, which I missed in case of pure iron, it also increased the ultimate tensile strength here, the maximum point, but it reduced the strain at fracture, strain at rupture. What does that mean? That means that its ductility, because ductility has to deal with the overall elongation or we can say that ductility depends upon the maximum strain or the maximum plastic deformation. Anyhow, the ductility of the material is reduced, the yield strength and the ultimate tensile strength, they are increased. If you add some more alloys, like some alloying addition, for example, chromium or nickel, we may expect that there would be an increase in sigma Y value, as well as there would be an increase in the ultimate tensile strength. But at the same time, you can notice that the elongation percentage at fracture or at rupture is less, which means the ductility is now reduced to a great extent as compared to the pure iron and carbon steel as well. Finally, if we go for the heat treatment, like for quenching and tempering of the same alloy steel or some other alloy steel, it doesn't really matter. The grades are written here, but that's not important for the moment. You take an alloy steel, quench it, temper it, and then perform the tensile test, and then eventually you will observe in most cases that the sigma Y value will be maximum. It will be more than any other type of steel as well as iron, and ultimate tensile strength, consequently it will also be more than the other ultimate tensile strengths at these locations. But the fracture point, it appears way too early as compared to the fracture in case of pure iron, carbon steel and high strength steel. Now you can see that the elongation percentage is less, which means that the ductility is reduced to a great extent. The common point, we have Young's modulus that remains almost constant. I would rather not say that the Young's modulus remains constant in all the type of steel. I would say when you change the composition, because naturally when you change the composition, when you change the structure based upon the heat treatment, the Young's modulus is because since it is a function of the material property, because it is a material property, it depends upon the materials inside the specimen which you are testing. So if you change the material, you add some carbon, even if it is in very low content, or you add some, let's say, alloy to it, some other additions like chromium, nickel, manganese, it is going to affect the Young's modulus. However, that effect will be very small. In most cases, it will be negligibly small, because mostly it is 80-90% or more than 90% iron. The significant effect is observed in case of plastic deformation region or the sigma Y, ultimate tensile strength and the rupture strength. Let's move on. So we can summarize our discussion by stating that strength is affected by alloying, heat treatment and manufacturing process, but stiffness modulus of plasticity is not, it's hard to say not, but it's negligibly small, it's trivial. Now, here we want to analyze in further detail what happens if we load a specimen of a ductile material to some plastic region and then we unload it. What happens? Let's find out. Let us suppose we have a specimen which can deform in elastic as well as in plastic region, and that specimen is also the ductile specimen. Since it's a ductile specimen, obviously we should observe some strain hardening up to this point, and then there is some decrease in the stress values because of the necking region. So we have a rupture state here. Now if you notice that when we started loading this specimen from location A, we moved to B, up to the point B, it was completely elastic deformation. Then we moved from B to C, which is a plastic deformation region, or we can say this is the region of strain hardening. From C, we stop at C and we decrease the stress, or we remove the force. What happens when we remove the force, or what happens when we unload the specimen? At location C, this specimen will, when we remove the force, it means we have removed all the stress. It will follow this curve to reach a point D on the epsilon or the strain axis. What does that mean? Well, this actually means the loading, first of all, in the region AB, it is elastic. The loading between the region BC is plastic, whereas the loading from C to D, the unloading from location C to D is completely elastic. Now that is a very interesting result. Why it is so? I would like to explain it in a bit more detail by drawing a straight line here. I hope it is straight enough. Now this line indicates it is passing through the point C. It shows a point here. Here I would like to mark it. This point. Sorry. This is the point of total strain. Initially, the specimen got the elastic strain, then it got the plastic strain. So we have total strain present from the location A to the to this new location, or on the curve it is the location C. To this point we have what we call as total strain. Total strain. Now this total strain is actually equal to the sum of elastic strain and plastic strain. We know that the characteristic of elastic strain is that it is recoverable. It doesn't matter at which point you, sorry about that. It doesn't really matter at which point you release the specimen or you remove the forces from the specimen, the elastic strain will be completely recovered, whereas the plastic strain is what that will stay, that will be left in the specimen. This shows that from point C to D, since only the elastic strain will recover, we can expect that the unloading will be completely elastic. If the unloading would be plastic, we should go back on this curve, but this doesn't really happen because the plastic is permanent. Plastic strain is permanent. This deformation will not be recovered. We will only have elastic recovery. That's why upon unloading we get the elastic curve, or the curve which resembles the loading region of the elastic curve. It is parallel to this curve from A to B. Moreover, when we reach at point D, we see that all the stress is removed. The stress is zero, but there is still some strain left. What is that strain which is now left? We call this strain as plastic strain. The strain between the region A to D will actually be the plastic strain, or the permanent set. And what region of the strain is recovered? It is actually elastic strain, which is here between the point D and this point, which I have marked with the help of a yellow circle. Now we can, the rest of the discussion is very simple. It can be seen. I can just move on to the bullet points. If the strain disappears, when the strain is removed, the material is said to behave elastically. The largest stress for which this occurs is called the elastic limit. We have already discussed what the elastic limit is. Elastic limit is the sigma y of the yield strength value. There is no difference between the two. What else? Wait. When the strain does not return to zero after the stress is removed, the material is said to behave plastically. And this is exactly what we have discussed here. When we remove the stress, the recovery, elastic recovery, is along this curve from C to D, and the remaining strain in the material is called as the plastic strain.